Hello, everyone, and thanks for joining Coffee with Vitex today. My name is Priya, and I'm the marketing lead here. Today's talk on 100G-ZR4 is presented by Eric Mack, Senior FAE. Eric has over 35 years design experience in the fiber optics communications industry. Over the last many years, Eric has helped customers in analog cable TV, DWDM long haul, and hyperscale data center applications. Today's presentation will be short, about 20 minutes or so. If you have questions, please type them in the Q&A box. The recording of this webinar will be uploaded on our website tomorrow. I'll be posting a link to the web page in the chat box. And now over to Eric.
Hello, everyone. Welcome to the webinar. Today, the topic for the webinar is QSFP28 100G-ZR4. So for nowadays, for the link in between 40 kilometers to 80 kilometers, application is point-to-point in between buildings and or between data centers, and or very short distance and a very high loss. The current solutions are Mux Pounder, which use 10G DWDM Mux demux going through 80 kilometers of fiber into an EDFA. And the second one is repeater, which we call it OEO. And the 100G data will go through 40 kilometers through a repeater and through another 40 kilometers of fiber. And third one is the coherent DWDM. They are in the form of CFP and CFP2. And the last but not the least, QSFP28 100G DWDM using PAM4. And the link has EDFAs and dispersion compensation network at every 5 kilometers or so. So you can see all those solutions are expensive. So what I'm talking today here is to offer a unique solution by using 100G-ZR4. Many of you already know, but I want to focus on the technical side of it today. So here's pretty basic, but I would, skip the minor ones, but and focus on the major spec. The form factor of the QSFP 100G-ZR4 is QSFP28. The data rate is 25 gigabits per second NRC. Keep in mind that's NRC, right? It's not PAM4. The configuration is 4 links or 25G, translated to 4 wavelengths at the 25G each, and then multiplexed together into a single fiber. The wavelengths are LAN WDM, as I have shown here. The power consumption and is about 4.5 watts at 35C and about 1 watt more at 65C. So we guarantee 6.5 watts here. So the next spec I want to mention is that without is the FEC, but without the FEC, the length would go to about 60 kilometers or so. With KR-4 FEC for NRC, the length can be reached to about 80 kilometers or so. So in order to achieve the 80 kilometer, you need KR-4 FEC. Very simply put, for KR-4 FEC, the coding gain is about 6 dB or so, which can improve the bitrate rate from 5 to e⁻⁻5 to better than 1 e⁻12, or you can extend the length from 60 kilometers to 80 kilometers. It depends how you look at it. So there are 2 questions, very obvious from probably from most of you. The first one is why not using 1550? The second one is why not using APD? And I try to address those questions by the following slides. First, I'd like to put that back together. It's a very typical chart. The first one is the attenuation of the fiber, which you know has 3 windows. One is for 850, the other one's for 1310, and the third one is for 1550. So as you see, the 1550 has a little bit less, maybe 0.1 to 0.15 dB less per kilometer of attenuation on a single mode fiber. So, and then the next chart is most important in this regard, or the KR-4. So it's called the dispersion penalty chart. As you can see, we call it a dispersion 0. It's at about 1310 here, but it's not actually 0. It has some finite value there. But let's for the argument is 0 dB here, 0 picoseconds here. And then, but as you move to 1550, it becomes about roughly around 17 picoseconds per nanometer per kilometer, right? So with all the characteristics I spell out here, so which is a standard single mode fiber. So the next area I want you to pay attention is the dispersion penalty. You can calculate it with this formula, plug it in everything, then you can plot a chart like that. So then the third area I want you to pay attention is the link, right? Here's a very simple formula, how much it can transmit with the wavelength, with also the data rates. I make it a highlight red bit rate, right? So bit rate is not just bit rate, it's the square of the bit rates, right? I just put it here to make sure you pay attention to this. And then also in order to calculate everything, you need also the dispersion penalty put in. So needless to say, when you do the 1550 calculation, dispersion penalty is pretty big. The transmission length would be pretty short. And I will show you on the next view graph, which I presented in another webinar, which is called OSNR and sensitivity in last year, October. You can go to the Vitex site to search for it. Basically, I present the same formula, and you can see the same formula is here, okay? But what I want to show you is the following charts, right? Here's the dispersion 0. But here is the link transmit, right? So the top one here is 10 kilometer, is 10G. Basically, I want to put it here as a comparison. The red dotted line is 25G. So you can see for usual line width of roughly 0.2 of nanometer or so at 20 dB down. At 25G is roughly, this is theoretical value, right? It's calculation. So it's roughly about 30 to 40 kilometers or so. So that's the best you can do for a given line width. So this slide, I try to address a second question, why not APD, right? We've been using APD for a long time, especially for the 10G link, and which from the metro to access network, as they are most cost effective than the PIN-TIA solution. However, the APD has a very poor gain bandwidth limitation. And then the dominant noise source is from the sharp noise. You can see roughly the basic formula here. You can Also, I highlight the bandwidth. Here is bandwidth, the bit rate, and so forth. It depends how you look at it. And that has some multiplication factors. Both of them are on the denominator. So you can see there is a trade-off. You want a higher speed, you're going to suffer with the lower gain, basically. And you can see the chart on the right-hand side. And up to a certain gain, and then it would drop down very sharply because due to the trade-off. So I look at what is available today, and I found that the best APD can do is about truly 30 to 40 kilometers at 25 gigabits per second. For NRC, especially they use on the ZR4 lights, sensitivity is roughly about -17, -18 dBm for the 1E to the -12. Or some link they use the PAM4, right, at the 25G. But the problem is using PAM4, you can only reach to the same type of distance. Again, you have to use KP4 for the PAM4 signal. That means it's a DSP-based design. Hard power consumption and expensive. So let's go back to the other solution, which is using the SOA. SOA stands for semiconductor optical amplifier, and which is basically when there is an external current thrown through, excited and incoming photon, as shown in the picture. The photon coming in, the electrical current thrown through. This electron, and when it mates with the interact with the incoming frequency, it would drop back to its original low power states. This energy loss in this process, it creates a new photon with identical phase, frequency, polarization, and the direction of the input photon. So simply put, it amplifies the input photon by using the current injection. A comparison in between SOA and APD is the SOA, the bandwidth is not contained by the gain. It's not. Secondly, the amplification of multiple channel, you can amplify multiple channel together in the optical domain instead, like the APD, and you amplify each channel in on the electrical domain. The third one is the dominant noise in SOA is the signal spontaneous bit noise instead of a sharp noise in APD, which I have shown is here's the sharp noise equation. So so the next picture I just show the application of SOA inside the receiver, and also this is cut and paste picture, and but it just mean to focus on how the difference is in between APD and SOA. So SOA amplifier in optical domain, the total optical power, and then there is a demux to demux all 4 channels into individual pin detector, right? And then TIA and so forth. So on the right-hand side, there's a chart to show roughly the with and without SOA, the improvement in sensitivity is roughly, this chart show about 9 dB or so. So here shows also a possible solution. Right now, we are on the right-hand side here. SOA on the receiver and then split, right, demux into 4 different channels. Likewise, and I think in the future, that there is going to be a usage of SOA in the transmitter because the 4 lambdas been muxed together in some system, and then you just put the SOA up in the front end there to amplify the signal. So we will see SOA more down the road as the speed start to increase. And just touch base a little bit on the performance. You can see, right, on this calculation, use the +2 dBm on the transmitter minimum, minus some dispersion. Like I said, the dispersion is finite, it has some values. Let's say below 1 dB. And then also you minus the sensitivity, you come up with a link budget about power budget, not link budget, power budget 29 dB. 29 dB, you minus some connector loss, it will translate to 80 kilometer of single mode fiber. So it's pretty typical calculation. This KR-4 can leverage the widely used already deployed in the field, right? You know the 100G product is most of that is 4 × 24 gigabits per second NRC, right? So when you use this without the need for optical amplification or dispersion compensation, it's very simple. Nothing is needed to change on the customer side, on the whole side. The large power budget, the 30 dB or so, can be pretty useful for a short distance with a high loss link. They just split it. And it should be used on a point-to-point interconnect routing application between the data center and between data center and central building without the use of complicated, power-hungry, and expensive coherent solution, or the legacy of CFP or CFP2. And here I conclude my talk by doing a summary. And I have overviewed the availability solution for the 40 kilometer to 80 kilometer applications and show the performance and specification for the QSFP28 100 gigahertz CR4. And I also explained the requirement for the 80 kilometer and 40 kilometer link, 1310 nanometer versus 1550 nanometer, and APD versus SOA, and also what the SOA is. And here's the end of my presentation. And are there any questions?
Eric, there is one question that I can read out.
Okay.
Can we use a dispersion shifted fiber to be used at 1550 nanometer?
Can we use dispersion shift fiber at 1550? Yes. Yeah, so that's another area you can look into it. And again, you know, dispersion shift fiber is not a free lunch, right? Because you shift per link, right? So the whole link is distance dependence, right? Anything you want to change, you have to re-optimize your performance. It's not going to be flexible, right? You can see it's a very, very link dependence parameter. Yeah. Compensation in a whole, this type of compensation is not flexible, but it can be done. Depends on the specific application. Okay, anyone?
Just one more question. What vendors are currently shipping the 100G-ZR optics?
We are shipping. That's why I list the part number. There are maybe, I look around, maybe there are 2 to 3 vendors right now in the market. And you can go to the website, you can see the availability. But If they are able to quote you with the cost or the price, that means they should be available. But some of them just show that they should. Yeah. But we're shipping.